Hello everyone and welcome back to the channel. Again we are continuing with this playlist idea 1C 2Q, where we do one concept and two questions related to that very concept in just a video. And the topic of interest for today is elastic versus inelastic collisions. This is like a subtopic of the forces and momentum section of your AS syllabus, and this confuses students a lot, so I thought why not make a video on this and help students out in the process. So first off, collisions are basically when two objects moving collide, and these can be categorized into elastic versus inelastic collisions. Now, what is the difference between elastic and inelastic collisions? In elastic collisions, we say this, that the kinetic energy is conserved. So elastic collisions, we'd say Ke is conserved. And similarly, we would say, and vice versa, for inelastic collisions, everything is the same, but Ke is not conserved, right? So this is the basic idea of elastic versus inelastic collisions. Oftentimes the examiner does try to confuse the students with these ideas, that what happens to the momentum or what happens to the total energy. Those are universal laws that would apply to all types of collisions, irrespective of whether it's elastic or inelastic. So always remember that total momentum and similarly total energy are always conserved. So regardless of whether it's elastic or inelastic, this always happens. Now, if I'm talking about a type of collision, let's say if I have a couple of objects here. So let's say there are these two objects which collide. One of these has mass is m1. It's moving with some initial velocity u1 towards the other one, which is mass m2, and it's also moving with some initial velocity. Right now, directions don't really make all that much of a difference. I'm just giving you an example right now. And then the collision happens somewhere in the middle here. So this is your collision. And after the collision, the objects shown have these velocities. So m1 is traveling backwards with this velocity v1, m2 is going forward with this velocity v2. So the idea is that the total kinetic energy before the collision would equal the total kinetic energy after the collision if it's elastic. So I would write the expression like this, that half m1 u1 square plus half m2 u2 squared equals half m1 v1 squared plus half m2 v2 squared. This is just the kinetic energy formula in action for such an elastic collision, right? So that's how this expression would be. Now, if we do some more math with this, then another sort of rule comes about, and the nice thing about that rule is that it does not depend on the mass really. Like this expression is not very easy on the eyes, but the other one is. We can also say that for an elastic collision, again, what we say is this, is that the relative speed of approach equals the relative speed of separation. Now, how do we calculate this? This is something to keep in mind. Is basically that, for example, in this case, and only in this case, this is not something to be memorized. And first, let me go through the rules that how do we write this. We say this, that if objects move in opposite directions, now opposite directions mean that either if one is moving to the right, the other one is moving to the left. This is what we mean by opposite direction. So they have different directions. We add for the relative speed. And similarly, if objects move in the same directions, we subtract for the relative speed. All right, now this is the mistake I've seen people making, because in the earlier part of this chapter, when you study momentum and collisions, and when you use conservation of momentum, and when you do questions related to forces, what people tend to do is that they also tend to assign signs to these. So they'd say this is u1, this is u2, but this is negative v1, which is wrong, because that's what you do when you are talking about velocities. But this expression clearly says it's speeds. So when you are already keeping this in mind with this rule that objects moving in opposite directions, you add for the relative speed of approach, objects moving in the same direction, you subtract for the relative speed of separation, this is already taken care of. Then you only need to play with the numbers that the examiner has given to you. You do not need to assign any signs to those. Now, for example, if I had to write it here, the relative speed of approach, I would say, is, for example, if u1 is catching up to u2, this means that u1 has to be greater, right? Otherwise, there would never be a collision happening. This would just be speeding away. So in this case, I would say that if u1 is greater than u2, they are moving in the same direction. I would subtract, and I would say this, that in this case, it would be u1 minus u2. This is the relative speed of approach. This is before the collision. And after the collision, they go away in opposite directions. So that would be the addition of 2. So that would be v1 plus v2. Right? So that's what this expression would become. Now just some general notes regarding elastic and inelastic collisions. And these are things that you don't really need to remember, but if you do, it can save you a lot of time and it can get you out of sticky situations. The first point being that sticky collisions, where objects stick or coalesce together, the sticky collisions are always inelastic. Always. There's always some loss of kinetic energy involved with these. Right? And again, that's just basically how the conservation of momentum works. And in that way, there's always some loss of kinetic energy. So sticky collisions always inelastic. Another one is this, that if objects of equal mass if they collide elastically, they exchange velocities. And again, this is also, it kind of follows through from the relative speed of approach equaling the relative speed of separation. And the idea is this, that for example, let's say I have this mass m, another mass m, colliding and then moving off in some way. So let's say if this one has some speed, let's say it's 3 meters per second to the right, this is 2 meters per second to the right. If they do collide elastically, the first one would now have a speed of 2 meters per second to the right, the other one would have a speed of 3 meters per second to the right. So these are just swapped for both the masses. And in this case, if I, for example, had to do relative speed of approach, that would be 3 minus 2. And in this case as well, it would be 3 minus 2. Because they're moving in the same directions, I would subtract for the relative speed. Now let's have a look at some related questions. So this first question is from 2018, paper 1-2. This is question number 9. So this one says an elastic collision occurs between two bodies x and y. Mass of body x is m, mass of body y is 4m. Body x travels at speed v before collision, speed 3v by 5 in the opposite direction after collision. Body y is stationary before the collision. What is the kinetic energy of body y after the collision? All right. Now this is what we need to figure out. So if this is an elastic collision, then I know kinetic energy would be conserved. Before the collision, this is at rest. So I can use conservation of kinetic energy for elastic collisions. I would say kinetic energy before equals the kinetic energy after. What's the kinetic energy before? That's just half m v square. Kinetic energy after, that would be half m, this time it would be 3v by 5 squared plus the kinetic energy of y, which is what I need to find out. So from here on out, this is just math. So half mv square equals half m into 3v by 5 squared. So half m, and 3 is the square of 3 is 9, square of 5 is 25, plus kinetic energy of y. Next step, you can just do some algebra. Kinetic energy of y would be half m v square minus this thing. There's a reason I didn't cross multiply, because I like to flex my mental math skills every now and then. I can just factor out the half mv square as common. So this becomes 1 minus 9 over 25, which is 16 over 25. So half times 16 over 25. This is 8 over 25. So that's basically 8 over 25 mv squared. And if you look at the options, then 8 over 25 is just a simplified form of 16 over 50. So that's C. All right, let's have a look at another slightly different type of question. This is March 2019, paper 1-2, question number 8. Two balls X and Y are moving towards each other with speeds of 5 and 15 respectively. They make a perfectly elastic head-on collision and ball Y moves to the right with a speed of 7. What is the speed and direction of ball X after the collision? No masses are given, so you cannot use kinetic energy. You cannot make any assumptions on the mass. So you'll have to use relative speed of approach equals to relative speed of separation. Don't treat this concept like an option that you could use kinetic energy. Oftentimes the question would be structured in a way to force you to use relative speed of approach equals relative speed of separation. So for the relative speed of approach, I see they're moving in opposite directions. So the relative speed of approach would be 5 plus 15. That would be 20 meters per second. So the relative speed of approach is 20. If it's elastic, relative speed of separation should also be 20. All right. So ball Y moves to the right with a speed of 7. And now we need to figure out what this would be, right? So what would be the speed of this guy here? Could be here, could be here. Now, if I think about the option to the right, so this would mean that the relative speed of separation would be 7 minus this, because this would have to move slower so that it doesn't catch up and collide again. So I would say 7 minus this velocity should equal 20, but this is obviously wrong because this is just the speed and speed cannot be negative. If I did try to do this, this would be 7 minus 20, which is 20. Sorry, this would be 7 minus 20. So that would be negative 27 again, which cannot be possible. So if we use the approach with it moving to the right, then this probably makes more sense, because here I would say 7 plus v, because they're moving in opposite directions, this equals to 20. So v would then be 20 minus 7, which is 13. So this is 13 meters per second to the left. So hope you guys learned something in this video. Let me know of more video suggestions related to the 1C 2Q playlist, and I'll be sure to also do something for that. So like, share, subscribe, and drop a comment if anything didn't make sense in this video. See you in the next one.